While most of the world's ocean has been getting steadily hotter under the pressure of a warming climate, one specific patch of the North Atlantic has been doing the exact opposite, and it just got considerably stranger still. Right in the middle of one of Europe's most severe droughts on record, that cold patch has expanded again. Scientists studying it just settled a years-long debate about what's actually causing it, and the answer points directly toward one of the most consequential ocean systems on the entire planet. Let's start with what this anomaly actually is, because it's been puzzling researchers for the better part of 2 decades. Just southeast of Greenland, there's a stretch of the North Atlantic that's been cooling steadily over the past 50 to 100 years, even as the rest of the planet's oceans have warmed dramatically. Scientists call it the cold blob, sometimes referred to as the North Atlantic warming hole, and it stands out precisely because it bucks the global trend so consistently and so visibly on every temperature anomaly map published over the past decade. For years, researchers have been split on exactly what was driving that unusual cooling, a genuine scientific disagreement that persisted across multiple studies and considerable debate at climate conferences. One camp argued the ocean surface in that specific region was simply losing more heat to the atmosphere above it, essentially a surface-level weather phenomenon that could theoretically reverse on its own without reflecting any deeper structural change. The other camp argued something considerably more serious was happening deeper in the ocean, that the currents responsible for physically transporting warm water into that region were weakening, delivering less heat to the area in the first place, rather than the heat escaping once it arrived at the surface. A team of international researchers, publishing earlier this year in Geophysical Research Letters, finally settled that debate using satellite data, ocean reanalysis records, and heat content measurements stretching all the way back to 1955. Their conclusion was unambiguous. The observed cooling trend simply cannot be explained by changes in surface heat flux alone. Instead, the data points directly to weakening ocean currents, specifically a slowdown in the Atlantic. Meridional overturning circulation, or AMOC, the vast system of currents that carries warm tropical water north toward Europe and the Arctic before it cools, sinks, and circulates back south at depth. The methodology behind that conclusion is worth appreciating on its own terms, since distinguishing between these two competing explanations required considerably more than a single surface temperature reading. Researchers had to reconstruct nearly 70 years of full water column heat content, combining historical instrument records with modern satellite observations and reanalysis techniques capable of estimating ocean conditions in periods before comprehensive direct measurement existed. That long, carefully reconstructed baseline is precisely what allowed the team to confidently rule out a purely atmospheric explanation, and instead trace the cooling trend down through the full depth of the water column, directly implicating the ocean's internal circulation, rather than simply the weather passing overhead. That finding matters enormously, because it means the cold blob isn't simply a quirky, cosmetic ocean anomaly. It's increasingly understood as a direct physical fingerprint of one of the most consequential climate systems on the planet, gradually losing strength. Researchers found the cooling penetrates the entire water column down to roughly 1,000 meters, a depth that corresponds almost exactly to the thickness of the northward flowing layer of the AMOC itself, further reinforcing the connection between the surface anomaly visible on ordinary temperature maps and the deeper circulation weakening quietly underneath it. Stefan Rahmstorf, the lead author of that study and head of Earth System Analysis at the Potsdam Institute for Climate Impact, research has been notably direct about what this means going forward. He's previously been skeptical of how quickly an AMOC shutdown could actually occur, treating the scenario as a genuinely distant, lower probability risk for much of his career studying the system. He now places the odds of an eventual collapse at over 50%, a striking shift in assessment coming directly from one of the field's most methodologically cautious researchers, someone whose credibility rests specifically on not overstating risk before the underlying data genuinely supports it. That kind of recalibration from a scientist known for skepticism carries considerably more weight within the research community than a similar statement from someone who had already been sounding alarms for years. Now here's where this connects directly to the severe drought gripping large parts of Europe this summer. Marilena Oltmans, an ocean and climate physicist at the University of Bremen, has explained exactly how a cold patch of ocean water thousands of miles away ends up reshaping weather on land. The cold blob creates a temperature front that acts like a guide for the winds and the jet stream, and as she described it, the jet stream ends up bending northward, flowing around Europe instead of directly across it. That deflection is precisely what allows a dome of high pressure to settle and lock into place over the continent, the exact mechanism behind this year's repeated record-breaking heat waves and the drought now stretching across huge portions of southern and central Europe. Oltmans previously led a 2024 study establishing the physical chain connecting Greenland's melting ice sheet to this exact outcome. Freshwater pouring off the ice sheet cools the surface waters of the North Atlantic, which then reshapes both ocean and atmospheric circulation patterns in ways that make Europe heat up considerably faster than other comparable regions of the world during summer. As she put it directly, that entire chain of events, starting with meltwater and ending with a heat dome parked over an entire continent, helps explain why Europe has become the fastest warming continent on the planet. If you're finding this kind of grounded, evidence-based breakdown genuinely valuable, go ahead and hit that like button. It makes a real difference, helping this channel reach more people who want the real science behind these headlines instead of vague alarm with nothing to back it up. This isn't a brand new relationship either, and understanding its history adds important context to why researchers are watching this summer's expanding cold blob so closely. A separate study published back in 2016 identified cold Atlantic anomalies as a common precursor to major European heat waves dating back to the 1980s, meaning this specific ocean-atmosphere connection has been quietly setting the stage for extreme heat on the continent for decades, long before most people had ever heard the phrase cold blob at all. There's also a genuinely strange twist buried in this anomaly's more recent history that's worth understanding, because it illustrates just how volatile and poorly understood this specific region of ocean remains even to the researchers who study it most closely. During the summer of 2023, a team of scientists, meeting specifically to analyze the cold blob's depth and robustness, discovered something none of them expected, a dramatic reversal of the decades-long cooling trend. The cold blob had suddenly warmed to roughly 2 degrees Celsius above its historical average, contributing directly to an unprecedented marine heat wave that researchers later connected to Europe's brutal summer that same year. That sudden reversal, followed by this year's renewed cooling and expansion, underscores just how genuinely unpredictable this specific patch of ocean can behave even within a broader multi-decade trend, and why scientists are reluctant to treat any single season's reading as a definitive, permanent signal on its own. So what actually comes next, now that this anomaly has expanded again during one of the most severe droughts Europe has faced in recent memory? Latest ocean analysis shows the cold blob growing further, with forecast data suggesting it could persist well into winter 2026 and 2027. The timing carries genuine significance because it's developing alongside a separate, historically powerful climate signal, a super El Niño currently strengthening in the tropical Pacific. Forecasters tracking both signals together note that the cold Atlantic anomaly combined with this strengthening El Niño could meaningfully alter the position and strength of the jet stream heading into the early stages of winter, with knock-on effects for storm tracks and temperature patterns across the United States, Canada, and Europe alike. It's genuinely important to be honest about the remaining scientific uncertainty here, rather than presenting every consequence as fully settled. Scientists broadly agree that AMOC is weakening as the planet warms, but genuine debate persists around exactly how quickly that slowdown could accelerate and whether an outright collapse is realistically possible within this century or considerably further out. What this newest research does establish with real confidence is the underlying mechanism, ocean currents, delivering less heat into this specific region rather than the water simply losing heat to the atmosphere above it, a distinction that matters enormously for how seriously the broader scientific community now treats the cold blob as a genuine early warning signal rather than a passing curiosity. The practical stakes tied to this ongoing weakening extend well beyond a single hot, dry summer in Europe. Researchers studying a full AMOC shutdown scenario describe consequences on a genuinely global scale: tougher winters across northern Europe, worsening droughts across South Asia and parts of Africa, and accelerated sea level rise specifically along the eastern coast of the United States, since a weakened AMOC changes how ocean water piles up against the North American coastline. None of those outcomes represents an immediate, imminent shift, but they represent exactly the kind of long-term structural risk that keeps climate researchers returning to this specific patch of ocean year after year, watching for precisely the kind of expansion now being observed. The combination with this year's developing super El Niño adds a genuinely significant layer of complexity to forecasting the months immediately ahead. El Niño typically exerts its own powerful influence over global jet stream behavior and storm tracks, independent of anything happening in the North Atlantic. When a strengthening El Niño signal overlaps with an expanding cold blob simultaneously reshaping Atlantic circulation patterns, forecasters face two major, partially independent drivers pushing on the same overall system at once, considerably complicating efforts to produce a confident, detailed seasonal outlook for the winter ahead. That complexity is part of why agencies tracking both signals have been careful to frame their early winter 2026 and 2027 predictions as directional hints rather than settled, high-confidence forecasts this far in advance. At the end of the day, A small, unassuming cold patch of ocean water southeast of Greenland has become one of the more closely watched features on the entire planet. Not because of its own temperature reading in isolation, but because of what that reading increasingly appears to reveal about the health of a critical ocean current system responsible for regulating climate patterns across 3 separate continents. Its expansion during this year's severe European drought isn't simply an unfortunate coincidence. According to the researchers actively studying it, it's a continuation of a documented pattern connecting a weakening Atlantic circulation directly to the extreme. Jet stream-driven weather now becoming an increasingly familiar feature of European summers. Whether this particular expansion phase persists through the winter, exactly as current forecasts suggest, or whether the cold blob delivers another sudden, unexpected reversal the way it briefly did back in 2023, remains genuinely uncertain even to the researchers monitoring it most closely. What has changed meaningfully this year is the confidence behind the underlying explanation itself, moving from a genuinely open scientific debate toward a considerably more settled understanding that this anomaly reflects real physical weakening deep within one of the ocean's most important circulation systems, rather than a passing quirk of regional weather.